How do you apply Fourier's law to real-world conduction problems? Imagine trying to figure out how much heat is leaking through a wall or how a computer stays cool. Fourier's law helps us understand how heat moves through materials. It might sound complicated, but it's really about simple relationships between temperature, material properties, and shape. First, you need to know what material you're working with. Is it metal, plastic, or concrete? Each material has a property called thermal conductivity. This number tells us how easily heat passes through it. For example, metals like copper have high thermal conductivity, while plastics are much lower. Knowing this helps you set up your calculations. Next, identify the shape or size of what you're studying. Is it a flat wall, a rod, or a layered structure? The shape affects how heat flows. For a flat wall, measure the thickness from one side to the other. The thinner the wall, the easier it is for heat to pass through. Then, measure or decide the temperatures at two points in the material. Usually, this is at the surface where heat enters and the opposite side where heat leaves. The difference between these two temperatures creates what's called a temperature gradient. The bigger the difference, the more heat will flow. Calculate the temperature gradient by subtracting the lower temperature from the higher one and dividing by the thickness. For example, if one side is 100 degrees Celsius and the other is 50 degrees Celsius across a 10-centimeter wall, the gradient is 50 degrees divided by 10 centimeters. Now find the cross-sectional area through which heat flows. If you're looking at a wall, this is the area of the wall's face. If it's a rod, it's the cross-sectional area of the rod. Larger areas allow more heat to pass through. Apply Fourier's law with the formula. Heat transfer rate equals negative thermal conductivity times the area times the temperature gradient. The negative sign just shows that heat flows from hot to cold, opposite to the temperature increase. Once you plug in your numbers, you get the heat transfer rate, which tells you how much energy moves through the material each second. This helps in designing better insulation, cooling systems, or even understanding how heat escapes from buildings. In steady-state conditions, where temperatures stay constant over time, Fourier's law works perfectly. For changing temperatures, you combine it with other energy equations to see how heat moves dynamically. For more complex shapes or three-dimensional problems, you use vector calculus and numerical tools. These help solve heat flow in irregular objects or systems with multiple layers. Practically, engineers use this law to figure out how much heat escapes through walls, how to cool electronic devices, or how heat spreads in engines. It's a simple yet powerful way to see how heat moves in many everyday situations. By understanding the relationships between temperature differences, material properties, and shape, Fourier's law makes it straightforward to predict and control heat flow in real-world problems.